Hi guys again, and welcome to the afternoon session, to the lab session, I should say, for today. Today is going, as I mentioned before, is going to be the last lab. There was another lab that was scheduled, but actually because we don't really, that lab works a lot better actually for in class than it does for the non-linear circuits. Basically what that lab that is we're not going to be doing, it has to do with the diodes. So in the lab, we will have a diode subject to small voltages, and we'll track the voltage, and we'll find for the first time a non-ohmic device, in a sense that V is not equal to a constant times I, because everything that we've been dealing with so far, really V equal to Ri, or V equal to Zi, or V equal to Xli, or V equal to XC, I, or something of this nature. In other words, those are Ohm's law, where the voltage and the current are proportional to one another. In a nonlinear circuit, like for example, transistors and diodes and things like that, that relationship is no longer true, in a sense that you will have a voltage that in one case, for example, is an exponential function of the, or the current is an exponential function of the voltage. And that is actually the case for the diodes. It is very hard to do online. I tried it. I did it actually in the past 2 or 3 times actually online, but it misses the point. In a sense, it's really not great. So I was hoping that somehow we can do stuff on at least on person, or have better animation, better basically simulation for it, but it couldn't. So therefore, this will be the last lab for this class. And this lab is all about the RLC circuit, really, in an AC power supply. Okay. So this is basically the lab for today. The instructions for the lab are on Canvas. There is a jar file, which is the same file that you guys have seen before. So hopefully you have had fixed whatever issues if you run into in the past regarding on how to basically enable Java on your computer. And basically install it first, and then allow it to open files like this Java file that we have in here for this lab. And that you were able to do it. Now, if you run into the same problem as before, probably reach out to me and hopefully we can solve it. If not, then I will probably suggest that you work with somebody who had it working. After this lab, you may choose to uninstall Java from your computer or secure it. And that's my recommendation for you, because Java is has had some issues in the past where people found vulnerabilities in it. So if you're done with this lab and you don't want to deal with it, you can, of course, uninstall it and remove it from your computer. However, if you secure it, you may also keep it there. So that's the only thing that is different for this lab. This lab is due not this Saturday, but the Saturday a week from this Saturday. So you basically have about 10 days to figure out this lab and do all of the activities related to it. And the grade there is basically out of 132 points. And you know the schema now. If there is asking you for a name, that is graded out of 1 point. Questions are on 2 points. The objective is about 3 points, is exactly 3 points. And the conclusion is 5 points. And now the tables, depending on the number of cells, each cell takes a point for its value, and the graphs are worth 6 points. The graphs will count only, 6 points. You get the full credit only when you include the labels, the points, the data points on the graph, and also the scales properly scaled. And also if it's asking you for trend line, you mark the trend line on the curve. So that is basically in a nutshell for the entire lab and how it's graded. And I think now you know all of these things were the last lab, so you should know. So the first thing you do, as typical for this lab, so you download the PDF file to your computer. Once you download it, it should be on your computer. And let me make sure that I have it, and here it is. So let me go into the share mode and share with you the PDF file. Okay. So again, typical stuff in here. Well, really, this lab was a little longer, so we're focusing only on the RLC circuit, okay? Don't forget the name. The objective, it's a good idea to keep it last, but don't forget it. Very important that you come back to it and fix it. This is an RLC circuit, basically. This is an RL circuit now, not an RLC circuit. Okay, you have a resistor and inductor, and we did this in lecture, and you have a square signal. So once you have a square signal, then this is the equation that you're going to be having in here. So if you use Ohm's law, you're going, Kirchhoff's rule, you start from any point. So you're going to go, for example, through the inductor that gives me L di over dt, that's the drop, the voltage drop, plus the voltage drop across the resistor, it's Ri, plus the voltage rise across the power supply, it's going to be minus epsilon is equal to 0. So the epsilon moves to the other side, and that's it. This equation, of course, has a solution, and we did that in the lecture, that is exponential of negative t over tau, where tau is actually L over R.
I think you're showing the wrong screen.
Am I?
Yeah, you're showing your internet browser.
Huh. Okay. Where is the... Sorry about that. Hold on. It's not good. You go through a whole thing. Okay, where is the... Okay, so let me go back in here, share, not screen 2. Was it the lab instruction or that you guys were looking at?
All we saw was your Canvas page.
Okay, the Canvas page. So where is now the PDF file? I don't even see it in here for some reason. I mean, I can see it on my computer, but for some reason I don't see it on the things to choose from to look at. Here. Do you see it now?
Yeah, we can see it.
Okay. So this stuff we did in lecture, the RL circuit, and this is what I was. The time characteristic is L over R. And once you solve that, basically, this is the RL part of it. So verify equation 1 is a solution. All you have to do is equation 1 is a solution to equation 2. It actually should be the other way around. Verify that 2 is a solution to equation 1. So basically, what do? Take the derivative with respect to time. The derivative of a constant is 0. The derivative of I naught is 0. The derivative of the exponential is just the exponential times negative tau. Negative 1 over tau, I should say. So the negative cancels the negative, and you will have 1 over tau times epsilon over R. Remember, tau is 1 over, it's L over R. So the L cancels, the R cancels the R. And then you will be left with epsilon over R, L, with a positive sign because the negative and the negative cancel. And you will have L times that. So you're going to be left with an epsilon times the exponential, basically. So the first term is easy. The second term is plus R times everything. R plus epsilon in here over R. R times epsilon over R is going to be epsilon. So that is going to be the epsilon on the other side. Plus R times this entire expression, which is Ri naught, times this whole thing in here. Don't forget you have already an exponential that will cancel in here. And oh, I'm sorry. This term in here, I was wrong about it. It's not just that. It's the exponential negative t over tau. Pull out the negative tau, but you have to multiply it by the whole term in here. So negative tau, which is tau, negative 1 over tau, which is negative R over L, and the R cancels the R in here. So if you do this, you're going to find it correct. Okay, let me do this quickly with you guys. Let me stop sharing quickly to show you how this works, because sometimes this thing can be a little bit. So let me prepare that and let me share. Okay, so we want to verify that I sub t, which is given to be epsilon over R plus I naught minus epsilon over R times the exponential of negative t over tau. And remember, tau is given as being L over R. In other words, 1 over tau is R over L. Okay? A solution to the Kirchhoff's equation for the circuit, which is L di over dt plus Ri is equal to the EMF. Okay, so let's take the derivative because we need the derivative in here. Okay, so the derivative of I with respect to t, the derivative of constant is 0 minus 1 over tau because that's how we find the derivative of the exponential times the exponential itself, minus t over tau, okay? 1 over tau is actually r over L. So this becomes negative r over L times I naught, minus times minus is plus, epsilon over r times r over L. The whole thing is multiplying that exponential of negative t over tau. Well, and here the r and the r cancel. And that is the only term that is left from this whole thing. Now, I have to multiply this entire expression by L in this term. So when I multiply by L, you can clearly see the L in the denominator is cancels. So L di over dt becomes equal to negative r I naught plus the only thing left in here, epsilon, and the whole thing is exponential of negative t over tau. So this is the first term here. Now I need the second term, Ri. Well, r times I is equal to r times I is given by epsilon over r plus I naught minus epsilon over r times the exponential of negative t over tau. Again, the r cancels this r, and it will be left with epsilon plus Ri naught minus epsilon, and this term is multiplying the exponential. And now I need to add this 2, and I need to check if they indeed add up to epsilon. So if I add them side by side, namely add this equation to that equation, so on one side, this should be epsilon, and my question is this the same on this side? So let's see here. I have negative r I naught plus epsilon times the exponential, that is the first term, plus the second term, which is epsilon plus r I naught minus epsilon times exponential of negative t over tau. Obviously, term by term, they cancel these terms. This is positive r I naught exponential of a negative t over tau. This is a negative r I naught of the same exponential. This is epsilon times the exponential. This is negative epsilon times the exponential. They cancel, and the only thing that left at the end is epsilon. Indeed, epsilon is equal to epsilon, and this checks the equation. So that, in a nutshell, the answer to the question. So let me stop sharing this screen, and let me share the PDF file again. Let me move this out of the way. So that answers this question, really, okay? And now we're supposed to go to open that jar file. So let me open the jar file on my computer and share that with you and start doing the activity. So downloading the jar file. The only option it gives me is to save it. So I'm going to save it to the lab folder, which is in your class. Spring 4B. Okay, I saved this right to the root, it's fine. And now I have to go and find it. Okay, and I have found it. Now I'm going to double click on it to open it, and it's loading. And after it loads, let me maximize it because I want to see it in its full glory. Okay, so let me stop sharing that screen and share with you now the jar file, the Java file, basically. Okay, so now for this lab, you need to use that jar file that is attached with this lab. Please set your lab as seen on the screen. So if you look at the screen in here, the first thing in here is show value. So I'm going to click on that, and I'm going to change it to schematic. And I'm going to pick up the voltmeter because we will need that. And I'm going to pick up a stopwatch because we will need that. And then what else? Do we need it in medium? It is in medium. And then I'm going to show extras and hide electrons because we don't want to see those dotted things. Okay. And in here, we're going to pick up a small resistivity just to make it more realistic into how it looks like. So that's all there is to it. Now I'm going to pick up an inductor. I'm going to pick up a resistor. And I'm looking at the other screen, of course. I'm going to pick up an inductor. Here's my inductor. I'm going to pick up a resistor. Here is the resistor. Here is the resistor. Okay. I'm going to pick up a switch. We need the switch. So here is the switch. I'm going to also pick up a power supply for this circuit, which is a DC power supply. So here is a DC power, so the regular battery, basically. It is. And then I have to pick up a bunch of wires as needed, okay? So this is one wire to connect this to. And this is another wire to connect this to. Did I duplicate it already? I did make it into a, I didn't know I had to do, I can do that, but apparently I did. Okay, anyway. Another wire in here. I need another wire in here. Okay, that is my circuit. Now I need to connect the voltmeter properly. So here is the voltmeter connected, and here is the voltmeter connected. The first thing I'm going to do is stop the play, pause it. So I'm paused it. Now I'm going to start the clock. Okay. Even though I started the clock, it says in here, it gives me the option to stop. Nothing is happening because I have everything in here paused. So that to control the time really, okay? Now it says to pick up an EMF of 12 volts. So the EMF right now is 9 volts. So I'm gonna right click on it and change voltage. And it's here, we can do it manually, we can. So we're gonna put 12 volts in here and click on and click back to make sure that it's stuck. And take a resistor of 10 ohms, and it is 10 ohms already. Take an inductance of 50 ohms, 50 henries. This is too big of an inductor, by the way, but because of this is a simulation, we can do that. Make sure the animation is stopped before you start the stopwatch, then start and stop the animation, record the values of the time and voltages across the resistor. At this point, there is no current going through the circuit. This is trying to push current this way. And in doing so, it's going to give me a, this one is going to oppose it. Since there is no current, the initial voltage should be 0. And as time evolves, the current starts to go higher and higher until this voltage should be around 12 volts in here. At that point, there will be no more changes in current because all the voltage drop is across the resistor. And there is no voltage drop across the inductor at that time because the current becomes steady. Initially, it's trying to increase, and then it becomes steady. As it becomes steady, di over dt approaches 0, in which case the voltage in here, which is LDI over dt, becomes 0. So that is basically what we're doing in here. You need to repeat the previous to fill the rows on the table. If I look at the table in here, and it's table 1, and count how many rows do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need about 10 points to fill out my table. I know the voltage is going to max around 12 volts. So I really need to be careful in here. When I start and stop, I don't want to start until it's almost 12 volts and then stop, and then I would hardly see any changes in the voltage. So I really want to see the first few volts stop and start and stop until I pick up those values. So here is the trick. Start it in here, not there, okay? Because there it's already started. So I'm going to play and then stop. After 0.5 seconds, it's still registering 0. And why is that 0 volts? Okay, because there is something wrong in my set. Oh man, I know why. Reset. Because I still have my circuit open. Hopefully you guys saw that. I need to close my circuit now. Okay, now we're ready. I reset the clock. Now if I start, the voltmeter starts to record voltages, okay? So I have to be careful with it. I have to pick up the slightest change in voltage so that would be my reading number 1. So start to stop. So after 0.39 seconds, I come back into the table and put the time in it and put VR. Make sense? VR right now has hardly a volt, which is fine, which actually is good, okay? Then I'm going to start it again. Now I have a different voltage after 0.81 seconds. It's a good idea to find out what is the time characteristic of this circuit so that you know roughly how long will it take for it to fully charge. Okay, is this step clear? How to fill out table 1? Okay, very good. As long as you, I'm not going to do the whole 10 steps because I really don't want you to rely on my numbers. I want you to do your own numbers, in a sense, fill it out. Once you find basically once you find your time and the voltage on the resistor on each step, you're going to do the calculation, ln of 1 minus VR over epsilon, which should be done on Excel if you want to. Once you find that value, you're going to plot that as a function of t, as a function of time. So basically, if I wait a long time, just to show you that this voltage reaches 12 volts and does not change anymore, because this is the power in here, there will be no more change in current at that point. The current becomes steady. So if I wait for a long time, the voltage is increasing now, 7 volts, 8 volts. It's going to slow down after a while because it's an exponential growth, 10 volt, and now it's slowing down actually, barely made it to 11 volts. So if I wait for a t equal to infinity, it should go to 12 volt. So now it's barely changing. This is 23 seconds. Okay. 30 seconds. It's hardly changing by decimal points in here. Okay. It's still changing, by the way. I mean, even though it doesn't look like it is gaining, but it is. Okay. It's going to take, because that's the nature of the exponential growth. It starts rapid, but then it starts to slow down. Okay. Typically, this value should really be 12 volt. Okay. But because I have finite probably resistance somewhere and things like that, that is why actually we took a small resistance. So it's actually less than 12 volt from the battery. So right now it's hardly changing. It's stuck at 11.36. Let me stop it and let me read the voltage, the actual voltage across the battery. And that is actually 12 volt right now reading. Okay. So it's interesting that we didn't get into. So how much volts we still have in here? Because this should drop to 0 practically. Right now it's 0, yes? So where is the other voltage? Is it in here? Or we still did not reach saturation? So let's continue. Oh, no. Remember, you're supposed to do it from in here, okay? You're not supposed to do it from the top in there. You have seen, it doesn't seem to be changing. Anyway, the point is, this is the exponential growth. Plot your data. If I reset that, is there a way for me to reset all values? Where is the reset all? Yes. Oh man, is that what it means? Sorry about that. And there is no control Z in here, by the way. Okay, let's see here what's the next questions in here, okay? So you do that, plot the function y, and y is not, by the way, the voltage across R. Y is just 1 minus the voltage across R divided by epsilon. And epsilon is 12 volt in here, okay? And in the graph provided on page 5, and page 5, if you look at the, let me stop sharing that screen and share with you the instructions, the lab instructions, if you can ever find them and not give you something else. Here it is. Okay. So again, this is y, which is 1 minus VR, and VR is whatever that value is divided by epsilon. Remember, epsilon is 12 volt, and at most you saw VR was 11.36. So this number is going to be less than 1. So this whole thing is going to be less than, it's going to be positive, more than 1. I mean, positive, in which case the ln exists, okay? So in which case the ln is some finite value. So you're going to plot that as a function of time on page 5. Where is the page numbers? Can I do the page here? Page 5. Here is page 5. Okay. So either use that, make sure the x-axis is properly labeled as time in seconds. The y-axis is properly labeled as a natural log of 1 minus VR over epsilon. And the plot, whatever you're going to end up with, remember the voltage was 0. No, the voltage, this is across the inductor. It was actually 12 volt, and it should start to decrease with time until it drops to 0, okay? So this should be in a decline. And use a linear fit, y equals to mx plus b, to find the slope m and the y-intercept of the plot. Compare m to a negative r over l. So it's going to be a negative slope. It's going to be coming down. And that slope should be in absolute value equal to r over l. Okay. If it's not, there is a discrepancy, then in this case, you know that there is a difference in there that you can explain, okay, between the lab and the experiment. And that is your error. So that is basically question number 2. And this is a graph, of course. Now, if you want to do it on Excel, please do so. If you can provide the Excel file, that's even better. And label your axis still and find everything in here. Now we're doing the RLC circuit. So we're done with the RL circuits. So the first part is done. Now we're going to do the RL circuit. Now what you have a capacitor, you have an inductor, and you have a resistor, and you have voltmeters that give you VC, that give you VL, and give you VR, and you have still that square signal in here, okay? And if you go through the math, this is how the equations look like. The signal in here, the power supply, is going to be a square signal. So if you solve for this equation, again, we did this in lecture, except I didn't call it gamma, I called it alpha. And this was actually lambda, r over 2l, or we call it tau at some point. And this is lambda squared or tau squared. And this is omega naught squared. 1 over LC is actually omega naught squared, okay? So this solution exists and is real if this number is more than that. If number is equal to that, we are at resonance. If this number is less than that, then we have oscillations with damping. And that is what we saw. So those are the 2 expressions. Okay. If you can do this, I'm going to make this one a little bit, loosen up a little bit. So you can go back to the lecture and try to understand that and basically copy a couple of pointers from there to here to show me that you know where these equations are coming from and that this equation, everything checks, okay? So this is the solution in general for the overly damped system, okay? When the initial condition at t equals to 0, q naught is equal to q is equal to q naught, and I equal to obtain an expression for b plus and b minus. Again, you don't have to really do it in detail. It's really long calculations. If you want to, go ahead and do it. If not, just show me how to proceed with this one, okay? Because typically there's a lot of algebra involved with it, because this is the deal. You have this expression. Don't forget you have gamma plus and gamma minus that are, or alpha 1 and alpha 2 as I call them in class, okay? Those are the 2 terms in here. Once you do that, then you put t equal to 0, q sub 0 is equal to q naught. So you have an equation that involves c epsilon plus b plus, because t equal to 0, this is just 1, and this is 1. So you have an equation that involves b plus and b minus. Then you take the derivative of this expression, which gives you I. Then I will become, this derivative of constant is 0. So the derivative in here is going to be minus gamma plus times b plus or minus gamma minus times b minus. And you have the expressions of gamma minus in terms of all of the other parameters, namely R and L and C. And now you have to equate that to I naught at t equal to 0. Again, you will have b plus times minus gamma plus minus gamma minus times b minus equals to I naught at t equal to 0, because the exponentials become 1. And then you have 2 equations with 2 unknowns, b plus and b minus, and you can solve them. Okay, you can solve them. Basically, you have used the initial conditions to check that these are actually solutions. Okay. Again, if you have difficulty with this one, just tell me how to proceed with this one in here in principle, and that's fine. Okay. Question 5. Using the circuit construction, this the one that we're talking about, constructing a circuit and a DC power supply of 12 volts, and RL equals to 10 ohms, L equals to 10 Henry, C equals to 0.04. How long does it take your circuit until it reaches its steady state? How did you design a circuit and reach to the previous conclusion? Obviously, it depends on exponential of negative R over 2L. So let's do it. Let me stop sharing that. And let me share with you the kit. And now we're supposed to have resistor. I'm going to put the resistor here. And I'm going to have an inductor, which is here. And I'm going to have a capacitor in here. So these are RLCs. And we need a power supply. So we need a power supply here. And usually, typically, we need a switch in here to control things. So let's put the wires now. So here is one wire. There is another wire. Here is a third wire. Here is a fourth wire. Here is a fifth wire. And I'm going to move this one to here and move the switch closer in here. That's fine. And now, is this paused? No, it's play. It's paused. So we're going to close the switch in here. And let's make sure that let me show the value still. Let me see, the voltage has to be 12 volts. So I'm going to change this one to 12 volts. Done. And we need the resistor to be 10 ohms, and it is 10 ohms. We need the inductor to be 10 Henry. So let me go into it and change it to 10. So it's all the way down. This is the smallest value we can have. And the capacitance to be 0.05. So change value. And the smallest value is this one. So basically, let me check this value. So now we have everything in here in the circuit. Okay. And we need, so right now it's running the time actually, and we need to start the animation and see how long does it take for it to reach steady state. It will reach a steady state when the voltage across any one of them doesn't really change. Let's go through the resistor in this case. Why is it still 12 ohms, 12 volts? Oh, because right now we just barely opened it, okay? So there is no current in the circuit, no nothing else. So it's the same voltage drop. No, but it should be 0 in here. How about this one in here? For some reason, it's picking up values in here that are no good. Maybe if we start this from scratch, it's going to work. But let's see here if what's going to happen. That's why I don't. It was 0 really, because now it started to work. Okay. Okay, so you have to stop it around this times in here and see if this is a good enough number for you in here or not. It really should happen around R equals to 2L, few orders of magnitude of it. R over 2L, remember R is equal to 10 and L is 10. So it should be around half a second. A few times of it, it's really when it becomes more or less this steady state, because it's not exactly R over 2L. It's an exponential that keeps on changing, but that exponential really is several times orders of magnitude. So again, you can repeat this expression in here. So let me reset the clock. And how am I going to do this? Can I discharge stuff in here from the circuit? No, I can't. So you have to do it again, okay? So this is the idea behind it. Oops. I didn't mean to close that. Man, I probably will need it again. Anyway, so let's continue with the instructions. The idea in here, it would be a few, maybe around 4 to 5 times, okay? 4, because R over 2L is about half a second, so around maybe 2 to 3 seconds, you should start to see less and less fluctuations in the value of the voltage. Okay, verify it. Please check it. Okay. Now the resonance, which is the main thing of this lab. So again, we have a power supply now that is actually oscillating, unlike the previous cases, which was a steady current. Now we have V naught cosine of omega t, and now the circuit is oscillating. So you have the same equation as before, except now the power supply is different. Once you solve for it, this is the same stuff that we did in lecture. Again, this is the reactance for the resistor, the reactance for the inductor, the reactance for the capacitor, and reactance for the inductor is omega L. The reactance for the capacitor is 1 over omega C. And the expression here for the phi, which is the arctangent of XL minus XC over R. And the impedance, which is the total thing in here, is just square root of R squared plus X minus L times the whole thing squared. And you have the voltage, and you have, they have the charge, you have the current, you have everything in here, except now the current is actually a cosine, and you have everything in here in the circuit because we started actually with the voltage being the cosine. So if we do that and sub in our equations, we got this trig equation. Okay, show algebraically that VL of t plus VR of t plus VC of t equal to V naught cosine omega t. You will need trig identities abound. Cosine of omega t minus phi is cos plus sin sin. Sin of the difference is sin cos minus cos sin. And the cosine of phi, which is the cosine of the arctangent of something, is just R over Z, and the sine is XL minus XC over Z, because it's coming from the triangle actually. And then here is VC, is this expression. Here is VR, which is this expression. Here is VL, which is expression. If you add them up, one plus the other plus the third, with this signs and everything else, if you add them up and use the trig identities that you know of, the cosine of the difference and the sine of the difference. Because guess what? You have the sine of the difference in here and the cosine of the difference in here. And if you're meticulous and careful enough, you're going to find on the other side, everything matches. Don't forget the value of Z in the numerator and the denominator that is going to cancel. If you're careful with all of the steps, you're going to find V naught cosine omega t. I think that would be very satisfactory if you do it, and you're going to hit big mark onto understanding this entire chapter. Okay, using just trig functions, using just a sine and cosine. If you're more at ease with complex numbers, use complex numbers. If you're not, then like we did it in lecture, we did it purely with geometry. You can do the geometry, but the geometry leave it for later. I want you really to see if you can do this trig stuff. Okay, basically, again, just a repetition of what I just said. Don't forget the Z itself and XL, and here XC are given. It's 1 over omega C square root of R squared plus square root of, plus open parentheses, omega L squared minus 1 over omega C, the whole thing squared, okay? Times the sine of the difference, and you need this expression for the sine of the difference. And the cosine of phi is R over Z, because you will have a cosine of phi. Because you're wondering, what am I going to get Z squared then? Because the numerator looks like it's going to be Z squared, then I have a square root in here. Am I going to get the square root out of this picture? Well, you have in here already an R over Z, and they have a Z in there. So that's going to be your Z squared. Okay, so the square root is gone by itself. The same thing, you have a sine of phi from this expression, and the sine of phi has also 1 over a Z in it too. So you're going to end up with Z squared in the denominator in here everywhere. So that square root is gone. Now you have an XC in the numerator. An XC in the numerator for the sine phi has an R in it. So you're playing with an R times XC. And the sine of phi, you actually have an XL minus XC. There is already an XC multiplying this too. So you will have an XC times XL minus XC squared. So the thing started to look now more familiar. This is just this term. Now you do the same thing for VR. VR is V naught R over Z times cos. Well, the cos of phi involves also another R. Multiplying the other R is going to be R squared divided by Z squared, because there is a Z in the expression itself, which is the square root stuff. And there is another Z coming from this cosine phi. This cosine phi, I should say. Now, the second term will have a sine phi in it, which is also 1 over Z times R. And if you do it careful with this one, you're going to get it impeccably. Does this step make sense to you guys? Or should I elaborate a little on it? Okay, this one of you seems to be confident with it. If you have difficulty with it, please let me know. Again, these are the values you will need. In oscilloscope data, this is taken from an old data. So we're going to take L equals to 10 millihenry, which is more realistic now than that, that animation or that simulation. R to be 5 ohms, and C, which is 100 microfarads, which is more realistic, and the power supply is 10 volts. We'll allow omega to remain as an independent variable. In other words, omega can change. If omega equals to 500 radians, all you have to do is, based on this value of L, is this a value of R, on this value of C, and in this value of V naught, you need to find XL. XL is going to be 500 times this number. XC is going to be 1 over 500 times this number. Z is going to be square root of this number squared plus whatever you find in here minus this one squared under the square root. So they're going to be your Z. Phi is going to be the arctangent of the difference of these two numbers divided by 5. VC is going to be this 10 divided by or multiplied by XC. VR is going to be R times, did I say VC is? Oh, we need I. We need I. We need I to find VC. I is going to be simply this V naught divided by Z. Once we find I, then we're going to multiply this I by XC to find VC. We multiplied by R, we multiply I by R to find VR, and we multiplied by XL to find VL. Enter your data into that table. So in here, to show me a little how you did some of the calculations, but you go into the table in here. And this is what you calculated. XL, XC, Z, Phi, VL, VC, and VR. So this is based on your calculation in here. So this is calculated values from question 7. If you go back to question 7, what is question 7? This is what that deal is. Does everybody understand how to proceed in here? You have L, you have R, you have C, you have V naught, and you were given gamma to being 500 radians per second. I mean omega, I'm sorry. Omega to be 500 radians per second. Now you have everything. So you can find from the get-go XL. You can find from the get-go XC. And you can find from the get-go what Z is. But you need, and Phi, you also do the arctangent of XL minus XC divided by R. But you need to find I to find VC. I is this V naught, which is 10 volts, divided by this Z that you just calculated. If you do that, then you can find VC. All you have to do is multiplied by XC. You can find VR. All you have to do is multiplied by R. You can find VL. All you have to do is multiplied by XL. And now go to this table on this page 12, I believe. Is this in the way? Yeah, page 12. To fill out this entire column. Okay. So having said that, let's go back into the next questions. Question 8. Basically, you're given this data now. So imagine that this is from an oscilloscope, and you are at resonance. This is the voltage across the inductor. These divisions in here, they're telling you 20 divisions, 20 volts per division. What I mean by that is, this is a division. This whole thing is a division. So there is 20 volts. So in this case, so from here to here is 20. So this is 10 volts. So this is a power supply. It's about 10 volts, basically. That's the whole thing. So 1, 2, 3, 4, 5. So this whole thing, the 5 steps from here to here is one division. So that means this is 20 volts. Half of that is 10 volts. So this is the power supply. This whole thing, then that means that this is what is it? 4 volts and 4 volts and this is half of that, that's 10 volts. Same thing now, I need to find this voltage for the capacitors. The voltage on the capacitor starts from here. So this is 4, 8, 12, 16, maybe 17 volts. That is the maximum voltage on the capacitor. For the resistance, it's less than 1, actually. For the resistance, it's barely about 3, maybe 3.5 volts. Okay, I cannot read more than 3, so I was going to say 3, but slightly less than 4 volts. For the inductor from here to here, it's also less than 4 volts. Okay, so that is the maximum voltage. Now the divisions also from here to here, this is 5 milliseconds. That means this is 1 millisecond, 2 milliseconds, 3 milliseconds, 4 milliseconds, 5 milliseconds. So in time, if I take any time in here, that is 1 millisecond. So this whole thing is 5 milliseconds. So that is how you read this graph, the data that you have from this oscilloscope. Now you have this data, you're supposed to answer the following question. To measure the period of a given wavefront, count the number of divisions for a complete wave and multiply this by the scale of 5 milliseconds per division for this case. What is the period T of the above wavefront? What is the frequency F of the waves? Do you have omega equals to 2 pi F, which is equal to 500 radians? If so, you have done this correctly. Basically, this is what the idea is. This is a period. Going from peak to peak is a period, okay? Or from 0 to 0 is a full period. This whole thing is 5 milliseconds. This whole thing is 5 milliseconds. So now I take count. This is 10 altogether, 11, 12, 12.5 basically milliseconds. That is the period T. The frequency should be 1/2, no, not 1/2, 1 over period, 1 over the period. The period we said, let me share with you the calculator. Stop share and share calculator. So remember, T is equal to, how much did I say? 12.5 milliseconds. So the frequency should be 1 over 12.5 times 10 to the -3, because a milli has a -3 in it. So that is the frequency. I need to multiply this number by 2 pi F to find the omega. So this number times 2 times pi. 502-ish, okay? That's how much I'm supposed to find. They say that if you find around this number, then you're in good shape. Does this make sense to you guys? Okay, very good. So continue with the lab instructions. So that is basically in a nutshell. We found the period and we found everything in here, and we made sure that the 2 pi, because once you find the period, you invert it, and now you have the frequency. You multiply the frequency by 2 pi, and you should find around 500 radians per second. Okay, measure the 0 to peak amplitude of the power supply. Do you get 10 volts? I already showed you that it's about 10 volts. Because the whole division is 20, so each one of them is 4 volts, and you go 1, 2, that's 4, and about halfway, so that's about 10 volts, okay? And then measure the 0 to peak amplitude of the capacitor, resistor, inductor. So I already did that for you guys. All you have to do is just make sure you go through that, and you know how much they're supposed to be. So basically, this is what happened. You know how much VL is supposed to be, you know how much VC is supposed to be, and you know how much VR is supposed to be from the calculations. You need to compare the two and tell me if they're correct or not, okay? It can be shown that XL is equal to R times VL over VR times, and XC is XC is equal to R times VC over VR, and Z is equal to V naught over VR. Using your measured values from step 5, and R is equal to 5 ohm, calculate XL, XC, and Z. Now, we need to calculate these things based on your measured values, using those formulas. So now, I have VL, I have VR, and I have VC. I have all three of them. So I should be able to find how much XL need to be. It's R times VL over VR. Okay. R times VL over VR. This is how much XL is supposed to be. Okay. R times VL over VR. Based on this value. Based on this value for VL and VR. The one that you just measured. You should be able to find an expression for XL. XL in here should be R, which is known to be 5 ohms. 5 times the ratio of this one over this one need to go here now. And then compare the two, because you calculated it already in theory. And now this is based on observation. You do the same thing in here. For XC, it should be VC over VR times 5 ohms. Now you have found that. And finally, Z should be R times V naught over VR. And you have V naught now. V naught is the one that you measured, which is about 10 volts, times VR times R should give you Z now. So you have all of the experimental values based on your observation, based on your measured values from this chart. Ideally, you have to print it, please, and use a ruler for your measurements, okay? Do not count on the way that I did it, okay? So you really have to use a precise measurements in here, print the page on your computer, and then do the measurements. And I would require that you include that as part of the lab activities, because that showed me that indeed you scaled your scale correctly, and you're measuring the actual volts. And if it is not 10 volts, but 10.1 or 9.8, please include that, because it's more accurate that way. You actually have done some sort of an experiment in here. In the lab, we would have done it better, but at least short of that, this is what we do. And even in the lab, if we have an oscilloscope, it's better probably to print it and then start to do it by hand, okay? Because that's no different than the actual lab, okay? So at this point, we have done everything. The phase angle phi refers to the phase angle between the power supply voltage and the current. Since the current can be found from the expression, phase angle is easily measured. So here is how to measure the phase difference, okay? Here is the current. It's actually across the resistor. When the current is at its minimum, the voltage is not at its minimum. It gets its minimum later. There is a delay in here, and this delay is in time actually. What is the? Let's look at the 0 point. Okay, this is 0 now. Oh no, I'm sorry. The resistor. What am I talking about? The resistor is 0 now. Okay. This is its minimum now. This did not reach its minimum now. So I can compare from here to where this one reaches its minimum. So this is the gap in time between them. This is the time difference between them. So I have 1, 2. With a ruler, I can find exactly, if I drop the minimum all the way to here, find it exactly where it lays in here. I know this is roughly about 1 millisecond. This is another millisecond. That's 2 milliseconds. And this is actually, let's say, for example, you find 2.5. If the difference in time is 2.5 milliseconds, okay, that's the difference in time. You have to multiply it by omega to find how many degrees that is, or how many radians that is. So 2.5, that is milliseconds, times 10 to the negative 3. The whole thing has to be multiplied by my experimental value. The one I found was 503, actually. I didn't find 500 radians per second. It's 503. So if I multiply it by 503, I find the phase difference is 1.257 in radians. I have to multiply this number by 180 and divide it by pi to find exactly how many degrees that is. So divided by pi. Let me share with you the stuff that I'm doing in here. Stop sharing. and share the calculator, because it's very important that you do the calculations based on your measurements. Okay, again, I found, according to my measurements, and I did not do them with a ruler. Hopefully you guys will be more careful than I am. So basically I went to the minimum in the resistor, which is the minimum in the current, and find when the next minimum in the power supply happens. And I measured the delay in time to be about no problem. I'm scheduled tomorrow, so maybe we can do it some other time, Rami, okay? No problem. Anyway, the point being in here is I have found the measured value to be 2.5 milliseconds. Here is 2.5 milliseconds times my measured value. Remember, this is how much I measured my angular frequency omega. If I multiply the two, I find this number, but that number, omega t, which is omega times time, is actually an angle in radians. Okay, so I have to convert that to degrees, because typically we're talking about this, especially since my calculator is set to degrees, and this is a calculated angle. So I'm getting it in degrees after I multiply by 180 divided by pi to be 72 degrees. Okay, now 72 degrees is the actual phi difference between them. Now I need to compare that to the table. Share. Remember, I used a calculator earlier to find what phi need to be. Now I have a new phi. So if I calculated this one in degrees, I better have this one in degrees if you want to compare apples to apples. If I see how much error I made in here. If this happened to be in radians, then I can leave the original number of 1.2575 to compare the two in radians. So that's the only discrepancy in terms of these things. And this is basically the whole thing on how to do this. 360 degrees by t, and that's the same point. Okay, once you have found that, you're done with this part. It's a long lab. It's nothing, because it's two labs in one actually. Okay, now this is basically the chart that we did in the class. Remember, r times I. So we dropped the I in here, that's all. It's fine. We have xl in here, which is omega times L. We have xc, which is 1 over omega c. And the difference between them is actually this difference. This is the difference between them. And when you add them up is a z. Okay, so, and this is just typical numbers in here, typical stuff from the lab. So based on the numbers that you have in here, in the space provided, you draw your phase. Now you have an actual omega, which is 10 millihenry, and you have a frequency of 500. So this length in here need to be 500 times L, and L is 10 times 10 to the negative 3. So now you do the math. And you're going to draw a line in here, and you have to have properly scaled value in here. And then you have 1 over 1000 microfarads, and in the denominator you also have, 500. So 1 over 500 times 100 times 10 to the negative 6. And that is going to be somewhere in here, properly scaled, of course, okay? And then the value of R is 5 ohms. So this distance in here, according to that scale, need to be 5. And this helps you with the scale. This round things in here helps you with the scale, so that you know roughly, because these are circles, and circles have the same distance from the center point. So these distances are similar in here, so that to help you with the scale. Now, once you find that, you're going to draw R, you're going to draw XS, XC, you're going to draw XL. Take the difference. If XL is more than XC, the difference should be here. If XC is more than XL, the difference should be here. In either case, connect this in a right angle triangle, and that's going to be your Z value. So whatever Z ends up to be, also you can find its measured value. You can measure how long it is. And based on that, you're going to measure the value of Z from this shape, measure the value of phi, which is just protractor, and you should be able to find it, okay? Between R and Z, do your results agree with question 6 and 7? In other words, this calculation, this table is in here, because that's exactly the data in here too. So now there is another way for you to check your answer too, using the graphical method, purely graphical method. This could be a question in the exam, by the way. This thing could be a question in an exam. So think of it as preparing yourself for an exam. I know the lab is long, okay? So I'm sorry about that. Anyway, for omega equals to 500, do you have any more capacity? Do you have a more capacitive or a more inductive circuit? Basically, which one is winning? Is this longer than the other? If this one is really winning, that means it's an inductive. If this one is really longer, that means it's a capacitive. If both of them are equal, you have actually the resistance in this case by itself. You are at the resonance in that case, okay? So that's the last question in here for this part in here. And data analysis, they give you a bunch of data in here. Make a semi-log of the above data and the graph provided. This is you're trying to plot now. This lab is long, okay? You have a bunch of data now, and you have different values for XL and XC, and different values for the, what is the plot that we need to do? There is another plot that I thought we should have to do in here. Oh, it should be after the conclusion. Here are the plots that we need to do. Basically, you have omega, not linearly. You have to use the logarithmic scale in here. And you're going to do also you're varying omega in this case, because omega you will have in this data that you're given. Let me go back to the data. Here is your omega. It varies from 1,000 to 10,000. So if you do it on a linear graph, it's going to be a nightmare. So you're going to take this, the natural log of these expressions in here, and you have VC, you have VR, you have VL, and you have 5 degrees. Okay. So what you're drawing in here is VC as a function of ln of omega and so on and so forth. Okay. And basically make a semi-log of the plot in the graph provided below. So in here, just make sure that you say that you did it in the bottom in here. If you're not sure about this one, you can use Excel, okay? It should really be not too hard to do in Excel. And then for values of omega, do VC, VR, and VL have a maximum value. You will see from the plot, or actually from the data. Let's look at VC, for example. It's 10 volt, 10.4. It's increased to 20 volts, and then it went down. So there is definitely a value around 1,000 where this number starts to become maximum for VC. How about VR? VR starts small, and then it becomes big in here, and then it goes back small again. So it looks for the same frequency. I have the same high VR also. How about VL? VL, it goes from small values and then reaches 20 and then drops back a little, and that's it. Yes, there is the same frequency in here. Phi is 0 at resonance. So this is actually the resonance value. Okay. So you can answer what is the value of Z at resonance. The value of Z at resonance is the square root of, again, it should be just the value of R, whatever R is. Because these two, actually, they cancel. VC and VL, they will cancel, because 20 minus 20 is 0. So at the end, you'll be just with the left with this 10 volts at the end, or R, which is in this case, whatever resistance that you have in here in the circuit, okay? So that is what is the value of phi at resonance? That's 0. You can look at it exactly from this data in here. It should be 0 at resonance, okay? What would you say that phi is at a maximum, minimum, or neither? That's actually, it's neither. It's a deflection point. It's really changing the curvature, the shape of it. Okay. Show algebraically from equation 4 and 5 that the resonance. So when you put omega equal to that value, which is 1 over omega c, all of these values should make sense. Okay. Because now, remember, this expression is square root of r squared plus xl minus xc squared, and those two are equal, so they cancel out. You will be left with square root of r squared equal to r. So this should follow through from the calculations, and VR is equal to V naught, because the other two, they cancel. It's clearly one of them is positive 20, the other one is negative 20, and they cancel, so that the actual voltage drops back to V, which is 10, okay? And for very small frequencies, then in this case, where is the table? The voltage across the inductor, because omega is super small in this case, is practically 0. So the square root of VC squared plus VR squared is just this value now, okay? square root of 100 squared plus 0. Which is basically going to be just about 100. Okay, so this voltage in here, about 10. Square root of 100 is about 10. And for high voltage, it's the opposite. 10 becomes in here, not in here. And that's the end of the lab. It's a long lab, I know. Sorry about that, guys. But I'm hoping that you guys can finish it and do it and enjoy it. Make sense? Okay, so I'm going to stop the recording. And if you guys want to work on it now, it's fine. I can wait for you guys. If you want to work on it on your own, you're more than welcome to do so. And you can leave and do it later on if you have a handle of it. If you have questions, please let me know.
Sounds good.
Okay, so I'm going to stop recording.